Hi friends, earlier we discussed a function is differentiable when we are able to calculate slope at all points of the domain of the function. Slope at all points of the domain, or we are able to calculate its derivative. Derivative is actually equal to slope, right? We are able to calculate derivative at all points of the domain. Then we call it uh, the function is differentiable. Right. So let us understand some graphical significance when we are not able to calculate the slope. Right. So if we are given a graph, how can we say that whether the function is differentiable or derivative exists or slope exists at a particular point or not? So for example, a point like this as a corner. One side of the graph is approaching one way, another side of the graph is approaching another way. So if we are taking this left side of the graph, then this pink line looks like the tangent. But if you are taking this part of the graph, this pink line, the second pink line. So this is 1 and this is 2. Right. This is appearing like the tangent. So at this point P, clearly there is no way of clearly identifying what exactly is the tangent. So at this point, we cannot tell what exactly is the differential or what exactly is the derivative, what exactly is the slope of this point P. So this function is not differentiable at this point P. Right, we call this a corner. So where one side of the derivative is differing with another side of the derivative. Right, now let us take this example. Right, so in this example, if one side you are approaching, right, you are getting plus infinity. So these lines, the slope is positive, slope is positive, slope is positive. The line is getting straighter and straighter, straighter and straighter, and it is approaching infinity. Whereas this slope is negative, this is more negative, this is even more negative. So we are approaching lines like this. Negative, even more negative, even more negative, and this is approaching infinity from the negative side. So one side you are approaching from plus infinity, another side you are approaching minus infinity. We call this a cusp. Right, this point. So here also we cannot clearly say what exactly is the slope. And at the same time, this is infinity. Right, infinity is not a slope. Right, so slope means a valid real number. Right, infinity is not a slope. So that's why here also we cannot say we know the slope. Right, so the derivative does not exist. So this function is not differentiable at this point P. Right, let us take one more example. This point P. Right, here the slope, though both sides the slope is same, but the slope is actually infinity. Right, here in this case, both sides infinity, but one side plus infinity, another side minus infinity. Here both sides either plus infinity or minus infinity, but still it doesn't matter. Right. So this is called a vertical tangent. This point, this straight line that we are getting, right? This is a vertical tangent. So then also we'll say, because this again, this is something like tan 90 degrees. Tan 90 degrees is not defined, right? Infinity is a symbol. It is not a number, right? So that's why the slope is not defined here. Just for convenience, we say infinity, right? For example, when we say limit of something is infinity, that means it's a symbol. It's not a value, right? So limit does not exist. Just for convenience or for understanding how the graph behaves, we show it as infinity, plus infinity, minus infinity. So in this case also, right, if we get a graph like this, then at this point, it is not differentiable, right? So derivative doesn't exist here also, right? In this case, this point and this hole, right, there's a break. There's a break in the graph. Whenever there is a break in the graph, the derivative doesn't exist, right? Whenever there is a break in the graph, so for a derivative to exist, for slope to exist, first of all, the graph has to be continuous. Okay, but that also doesn't guarantee. Even if a graph is continuous, we cannot say that the derivative exists. So for example, this graph is continuous, but here the derivative doesn't exist. This graph is continuous, but at this point derivative doesn't exist. Slope doesn't exist, right? This graph is also continuous, but it doesn't exist. This is also continuous, it doesn't exist. but without continuity, right? If it is not even continuous, there is no way the derivative exists, right? Now here also is the same problem, right? Though there is a pole here and limit exists here because both sides we are approaching here, but limit is not sufficient. So limit of a function as well as the value of the function should match. So the graph has to be continuous first. At the same time, the graph has to be smooth. Differentiability means, slope means the graph has to be a smooth curve. Then we say, informally saying it has to be a smooth curve. Then we say the derivative exists. Right. So we just discussed differential functions are continuous. What does that mean? A function, if it is differentiable, it has to be continuous. There is no way a function which is not continuous, we can have, it is differentiable. Differentiable means all points in the domain, not just one or two points. All points in the domain, there should be derivatives at all the points in the domain of the function. That means the slope we can calculate at all points. Right. Now, let us look at some examples. In this example, we can calculate slope at all points. So it is differentiable everywhere. This is also very smooth. Right. This also is differentiable everywhere. Here there is a break. Right. There is a break. It is not even continuous. So it is not. Here, at this point, there is no, we cannot calculate slope because one side is something, another side is something. This point is breaking. Zero, this thing, this point is breaking. This point where it is not continuous. So this point also it is breaking. Okay. Here, this point. So there is a cusp. So that's why it is breaking. One side there's one slope, another side another slope. These 2 points, that's why it is breaking. So here, both sides infinity. One is approaching minus infinity, another is approaching plus infinity, and at the same time, vertical tangent, one is approaching minus infinity, another approaching plus infinity. So here also slope is not defined. So here also derivative doesn't exist. This is kind of cusp, right? So if you notice, all these places, these are not smooth. Smoothness is a criteria for differentiability, but derivative exists. This one is actually very smooth, right? This straight line is also kind of smoothly connected, right? Right, guys. Now that we have understood some graphs and some slopes, right? Graphs and slopes, let us try to match. These pink ones are slopes and these blue ones are graphs. Okay, let us try to match which graph can have which slope. Okay, so look at this graph. This graph, let's say this point is A, this point is B, this point is C. Okay, at A, what is it? The slope is negative. At A, slope is negative, at B, slope is 0. So at A, slope is negative, at B, slope is 0. At C, the slope is positive. So it looks something like this. That is this graph. Okay, that is this one. Okay, now again let's take this point A, B, C. At A, the slope is positive. See here, this is slope. The slope is positive. The value of the function is negative, but the slope is positive. At A, it is positive. At B, it is 0. Right, at B, it is 0. And at C, again, it is positive. So it looks something like this. Okay, that is this graph. Okay, this graph is actually A. This graph is actually B. So these two are done. Now let us look at this. Here, this point is A, this point is B, this point is C, this point is D, this point is E. Okay, so at A, the slope is negative. Okay, at A, somewhere the slope is negative. And at B, the slope is 0. Right, the slope is negative. The slope is negative and it is becoming 0. At B, it is becoming 0. Something like this. Now, at C, again it is becoming 0 and between B and C, it is positive. Right, between B, the line is like this. The slope is positive. Slope is increasing for some time and then again decreasing. Right, between B and C, this is B, between B and C, the slope is always positive, but at C, it is becoming 0. Right, so it is something like this. Right. Now, between C and D, it is always negative, but at D, it is 0 again. So it is something like this. Okay, at D, it is again 0 because the slope is like this. At C also, it is 0. The slope is like this. C is 0, D is 0. And again between D and E, it is the slope is positive, but at E, it is 0. Right, it is like this again. Sorry, my bad. This graph is actually slightly hidden. This graph is something like this. Okay. And this, I have shown till this part only. This graph is actually something like this. So there is this point. There is this point, say for example, some O also. Okay. So at A, this graph is like this. So that means at A also, the slope is actually 0. Okay. At A also, the slope is actually 0. And at O, the slope is positive. It is positive and it is becoming 0. Right. So the slope is positive at O and it is becoming 0. Right. So basically at O, the slope is positive. At A, it is becoming 0. That is this point A. And then, and then at B, again, it is becoming 0. Between A and B, it is negative. That's why this is negative. And at B, it is becoming 0. Between B and C, between this point and this point, it is positive. And at C, again, it is becoming 0. It's a flat line, right? And between C and D, at D, it is becoming 0. So between C and D, this line is negative slope, right? So that's why it is like this. And then between D and D, it is positive, but at E, this is becoming flat again, right? So this graph is actually this graph. This point is O, then A, then B, C, D, uh, C. At O, it is positive. At A, it is 0. At B, also, it is 0. At C, it is 0. At D, it is 0. At E, it is 0. Okay. Now let us look at this graph. Here, the slope is negative. This point is A. Let's say B, then C, then D, then E. The slope is negative. So, negative. At B, it is becoming 0. At B, it is 0. This point is 0. Then between B and C, this line is positive slope. Right. So between B and C, and again at C, it is becoming flat. So between B and C, it should be positive. Right. The graph will look something like this. Okay. Between C and D, it is negative. Between C and D, it is negative, but at D, it should become 0. At D, it should become 0. Between C and D, it is like this. And then after D to E, it is always positive. D to E, it is always positive. So the graph will look something like this. Okay. The graph is actually C here and D here. Please note here the graph is actually slightly missing. There is one more curve. Otherwise, it will not match this. Right. There should be one more curve. At A, it should be 0. That means there is a slight more curve which I have forgotten to include it properly. Right, guys. Hope you understood how to read graphs and slopes. For example, the slope of this line is positive, right? And slope of this line is negative, right? Please note the slope of this line. This is theta, tan theta is positive, and the slope of this line, tan, this is 90 plus theta, right? This is in the second coordinate. When the tan crosses 90 degrees, so this slope is negative. So slopes of lines like this, these are negatives. And slopes of lines like this, these are positive slopes. Okay. So it is very, very important to understand slopes of different curves, different graphs, how the slopes look like. Okay. This becomes very important as we go forward. We should know by looking at the graphs, we should be able to draw a rough sketch of the slopes. Right, guys? Hope you like this. Thank you.